Today's video will be about drawing Fischer projections. Before jumping in, identify the longest parent chain that contains the carbon. This is going to be the vertical line of our Fischer projection. And make sure when you draw your Fischer projection, make it a really big drawing because you will be assigning priority groups that get messy later on. Now, carboxylic acid can be expressed in two ways. It can be written this way, or it can also be written like this. But in this one, we'll just use a normal version to keep things simple. Now we have to add lines for each substituent that we have. So this line, this intersection, is representing carbon 2. And carbon 2 is attached to an OH and an H. Now, wedges and dashes do not automatically correspond to left or the right of the Fischer projection. You have to check their R and S configurations, so assigning priorities. This is 1, this side's 2, this side is 3. So this would therefore be an R rotation, and I like to add a little note saying that it looks R, because sometimes you invert things around. So if it looks like R, we're gonna have to draw something that looks R here too. Now this was our second priority and here was our third. So in order for it to be R, we gotta draw something counterclockwise so it looks as though it's actually R. So I'm gonna put this OH here. So this is gonna be counterclockwise. This is gonna be counterclockwise so it looks S, so it's actually R. As for the bottom here, same thing. Priority 1, 3, 2. 2's down here. 3 is still up. And here, okay, so R was on carbon 2. Carbon 3 is going this way, so it looks R. So it's actually S. Okay. So I want to make a quick comment here. This is meso compound, in case you've noticed, because one is R and the other one is S. Okay, one is R, one is S. They have a plane of symmetry, the groups are the same, and the R and the S cancel out the chirality, so this compound is a meso compound. Because when you draw, you'll find out their groups on both sides are the same. So now, I like to write it looks R just in case, because that makes things easy. So now, on here, we have to draw something that looks R as well, so it's actually S. In order for it to look R, our OH is going to be here. So this will give us a rotation that looks R, which is actually S. Yeah, so that's the first problem. Now we're going to level up. We're going to level up. All right. So for this problem, we identify the longest parent carbon chain. And I want to emphasize that our parent chain actually ends right there. It does not end on a BR, okay? So the vertical line is always going to be the carbon, never anything else unless they specify that they want something else at the end. So I'm going to say it's carbon, and it is actually bonded to 2 other hydrogens and a bromine. But actually, let's put this side on the top. So I'm gonna, no, actually it's fine. Okay, so we got an alkene at the bottom. So how do we express alkene? What we can do is, we can call this an intersection, and then there is an H bonded here. So this is going to be our carbon, and then we're going to add an H on one side and the alkene on the other side, which is also bonded to two hydrogens. So this is here. Okay, so you see this is our carbon of reference, carbon of reference, so two groups are bonded to it. Perfect. Now let's work from the bottom up. The OH, this is priority 1, 2, 3. Let's call it on a wedge. This is going R. It looks R as well. So we've got to draw something that looks R, and because the alkene was our priority 2, and the middle was priority 3, in order for it to be R, we have to draw something counterclockwise. So counterclockwise. Okay. So I'm gonna put OH on this side so that this looks counterclockwise. So in reality, it's actually R. As for the top, there are a few more hydrogens. And that is a solution for this one as well. And if you want to check, if you decided to make your top starting here instead, you could flip this Fischer projection, like rotate it 180 degrees to check that it's actually the same compound in case you drew it the other way. Never do anything fancy to a Fischer projection except rotating it by 180, okay? Only 180. And never anything else that is cool. Just flip it by 180. That's the beauty of it. Okay, our last problem. Once again, we find our longest carbon chain. Stops right here. Starts here, stops here. Okay. And I really wanted to emphasize that because it's easy to just make this end the vertical of the Fischer projection, but that's not usually correct. So we'll start from this side again. There is a carboxylic acid. We can write COOH, or the other fancy way is to do this. Okay, and then down here we have an OH. This is priority 1. This side's 2. This side is 3. This is going this way. It looks R, but it's actually S. Yeah, it's S. So we're going to draw something that looks R as well. Since this was our priority 3, this is priority 2. In order for it to look R, we have to start here. Once again, when you draw your Fischer projection, set it up so there's lots of space between every line so you can have more space to write your priority groups. As for the bromine here, this is 1. This side is 2. This side is 3. It's going R direction, and it looks R as well. Looks R, and at the bottom we have an CH2OH, right? CH2OH, or there's another way to write it, which I'll show you in a bit. Okay, so this is gonna be priority group 3, that side's 2, and in order to be R, we have to think backwards. It looks R, so we have to draw something that looks S. And if we do this, this is 1, this looks S, so it is actually R. And this is not a meso compound because there's no plane of symmetry. Now, as I said, the other way you can draw the bottom is a little bit weird, but it does exist and it is correct. So we ended up here, and we just do something like this. So this indicates that there is a carbon and there are 2 hydrogens attached to it implied, and the OH is still there, so that's also fine.